Welcome to the class. In this unit of work, heat and first law of thermodynamics, in this third lecture, we will discuss the development of further topics, and we have already described these terms: the concept of work in thermodynamics, adiabatic work, that means work done under adiabatic conditions, and from the concept of adiabatic work, we have developed the concept of internal energy function, and based on adiabatic work and diathermic work, we have formulated the first law of thermodynamics, that means the mathematical formulation of first law of thermodynamics. And from there we have the concept of heat, and also we have discussed the differential form of first law of thermodynamics. And now we have already the concept of extensive and intensive variables. We know that these intensive variables are independent of size and mass, and these extensive variables depends on size and mass. And as you know, the examples for intensive parameters or intensive coordinates are pressure, temperature, etc. etc. And that of extensive variables are volume, internal energy, etc. And normally in mechanics you will be writing work done as force into displacement. So we have a general idea that in the concept of generalized coordinates, extensive variables are displacement like quantities and intensive variables are force like quantities. So generally you are writing as force into displacement. And here you can see that for a hydrostatic system, we have written the expression for work done as minus PdV or simply just PdV. In that P is an intensive quantity and V, or that means dV, is an extensive quantity. That means the extensive variables are displacement like quantities and intensive variables are force like quantities. That means you are writing as F into ds or F dot ds. So in place of that ds, here we are writing dV. In place of F, we are writing P. So our intensive variables are force like quantities and extensive variables are displacement like quantities. And this is the case of hydrostatic system. And in our syllabus, we have to discuss only the hydrostatic system. In thermodynamics, you can generally consider an electrochemical cell, surface film, etc. as thermodynamic systems. There also, you will be writing one term, one intensive quantity in place of force and an extensive quantity as d into that dv. That means like that change in that quantity, d of that quantity, and that product will give you the expression for work done. This is a general criteria that we are considering in thermodynamics. So the product of the generalized force and generalized displacement gives the generalized work. And the concept of heat is already known to us. Heat is either internal energy or enthalpy in transit. This is a chemistry version actually. So you can say that it is either internal energy or enthalpy in transit. That means when heat is flowing out of a system, you can see that its internal energy is decreasing. So it is a flow of its internal energy. Similarly, if it is going into the system, that is becoming a part of its internal energy. So it is either internal energy or enthalpy in transit, depending on the experimental conditions. And uh, which quantity is flowing, internal energy or enthalpy? We have you have already the concept of enthalpy from chemistry, and in our coming chapters we will usually discuss that term H, enthalpy known to you as U plus PV. We will deal them later. So heat flow takes place only by virtue of the temperature difference. So that heat is either enthalpy flow or internal energy flow. And this is an important point. The performance of work and the flow of heat are methods by which the internal energy or enthalpy of a system is changed. That you can see. That means we have already seen that when you are performing work on a system, simply that means it may be either adiabatic work or diathermic work. In adiabatic work, we have shown that the adiabatic work equal to change in internal energy. So that work done, that means you are performing work on the system, and when that work is reaching the system, it is converted as its internal energy. In the similar way, according to our first law of thermodynamics, that UF minus UI, change in internal energy, you can write as W plus Q. So that UF minus UI depends on Q also. That means what either work or heat done on a system or by the system is converting as, or that quantity is appearing as a change in internal energy of a system. This is an important concept. And it is impossible to separate or divide the internal energy into mechanical part and a thermal part. That means you can't say how much portion of its internal energy is due to work and how much portion of its internal energy is by the performance of or by the transfer of heat. That you can't say. This is also an important thing. That means uh, outside the system you have heat and work, and when it is uh, performed on the system, it is becoming internal energy. And as a as an example for this, you may consider a problem like this. The amount of water in a lake may be increased by action of underground springs, by inflow from a river, and by rain. That means the amount of water in a lake can be increased by springs. That means water flow from ground, underground, by inflow from a river. So a river is flowing into the lake, and also by rain. So you can have three intakes. It may be decreased by various outflows and by evaporation. That means there can be outflow from the lake as well as it can be evaporated. So the question is simple. Comment on the question. How much rain is there in the lake? Can you say how much rain is there in the lake? That means if you can say if for 1 hour there was rain and that much quantity has reached lake, but uh, you have evaporation from lake, and you can't say only the water reach the lake by inflow from river is evaporating and only by rain is going as some outflow. That you can't say. That means all these are forms of water. So all are water, and this you when they are reaching before reaching the lake, they are naming as spring, then river, then rain, etc. But when they are reaching the lake, you are saying that it is the water in the lake. It is like the concept of internal energy of a system. Clear? So, how much rain is there in the lake? That means you can't say, or that question is not a correct way. It is absurd. Similarly, how much water in the lake is due to rain? That is not also correct. And what concept is analogous to rain in the lake? So you can say that it is like our internal energy. So internal energy means internal energy can be increased or decreased by the performance of either work or heat. In general, the work done on or by a system is not a function of the coordinates of the system, but depends on the path along which the system was brought from an initial to final state. Exactly the same is true of the heat transferred to or from a system. That means heat Q is not a function of thermodynamic coordinates but depends on the path. So our Q is also a path function that we have mentioned. So that is why you are writing as d bar Q and d bar W. And the general way of writing the first law of thermodynamics is in left hand side you are writing as du, that is an exact differential, and in the right hand side d bar Q and d bar W, they are inexact differentials. So you are separating exact and inexact to two sides. Now imagine a system A, this is system A, in thermal contact with the system B. That means here you can say a diathermic or conducting wall separating system A and system B. And the composite system, that means A plus B, are surrounded by adiabatic walls. So this is adiabatic wall, this is a diathermic or conducting wall, this black one, and this is adiabatic wall. So for A alone, you can write first law of thermodynamics as UF minus UA equals Q plus W. And for system B, you are writing it with the prime letters. That means UF prime minus UA prime equals Q prime plus W prime. And adding, you will be getting as UF plus UF prime minus UI plus UI prime equal to Q plus Q prime plus W prime. This is the expression we got. So since this UF plus UF prime minus UI plus UI prime is the change in internal energy of the composite system, that means A plus B, and W plus W prime is the work done by the composite system, it follows that Q plus Q prime is the heat transferred by the composite system. That is clear. So it is a total heat transferred by the composite system. And since the composite system is surrounded by adiabatic walls, what you can say? No heat can flow out of the system or no heat can flow inside the system. That means definitely that Q plus Q bar or Q prime equal to 0. Q plus Q prime equal to 0. Or Q is equal to minus Q prime. In other words, under adiabatic conditions, the heat lost or gained by a system A is equal to the heat gained. That means if A is losing heat, B is gaining heat. That is the meaning. The heat lost or gained by a system A is equal to the heat gained or lost by the system B. And this is known as the principle of method of mixtures. This is the equation that you are normally using in solving problems in heat. And now we are applying our first law of thermodynamics to heat capacities. We have already defined the term heat capacity. And for a hydrostatic system, the first law can be written as, That means generally you are writing as first law as du equals d bar q plus d bar w. And for a hydrostatic system, you can write d bar w as minus p dv. So du will be equal to d bar q minus p dv, or d bar q equals du plus p dv, where this u is a function of any two of p, v and t that we have mentioned so many times, since pv is equal to nr. And choosing t and v, you can write as, we have already mentioned this thing, that means u is generally a function of p, v and t, and you can write it as function of any two. And if you are considering the system as an ideal gas, then you will say that you will depend only on t. So you can write as du equals dou u by dou t at a constant volume into dt plus dou u by dou v at a constant temperature into tv. So now in place of this du, you are substituting this expansion. So your d bar q will be this plus pd. So that dv is common to both p and this d bar u by, or dou u by dou v at a constant temperature. So your equation for d bar q becomes dou u by dou t at a constant volume into dt plus dou u by dou v at a constant temperature plus p into dv. And dividing throughout by dt, our equation is now d bar q by dt equals dou u by dou t at a constant volume plus dou u by dou v at a constant temperature plus p whole into dv by dt. This equation is true for any process involving any temperature change dt and any volume change dv. Now we consider two cases. And the first case, v is constant, that is dv is equal to 0. dv is equal to 0, you are normally calling it as an isochoric process. So when dv is 0, this term is 0. So this whole term becomes 0. So you can write as d bar q by dt at constant volume is dou u by dou t at constant volume. And now what is this quantity d bar q by dt? We have already mentioned the specific heat capacity as heat, that means delta q by delta t. You have written that equation. And when it is at a constant volume, you are calling it as heat capacity at a constant volume. And when it is at a constant pressure, so normally you are defining heat capacity as amount of heat energy required to raise the temperature of a substance through unit change, that means 1 Kelvin or 1 degree Celsius. So this term is clearly heat capacity. Notice that the term on the left is an experimental quantity, the measurement of a small amount of heat transferred due to a small difference in temperature between the system and the surroundings during a process in which the volume of the system is held constant. And the term on the right is a derivative of the internal energy function with respect to temperature, while the variable volume is held constant during the differentiation. And the term on the left, by definition, is heat capacity at a constant volume Cv. That is, you can, this quantity you are writing as Cv. So Cv equals du by dt at a constant volume. Du by dt at a constant volume. And if P is constant, what happens? Our equation first becomes, in place of volume, you are changing it as pressure. D bar Q by dt at a constant pressure equals du by dt at a constant volume, because you are not changing this quantity, because this is already a differential with the constant volume. Du by dt at a constant volume plus du by dV at a constant temperature plus P, and here it is dV by dt at a constant pressure. You are writing like that. And this quantity dV by dt, And when it is at a constant volume, you are just this dV is 0. But when you are considering another variable with these quantities P, V and T as P, so this V is changing with respect to T at a particular pressure. So you have to write this as dV by dt. That is the more correct method. That is why here you are writing it as dV by dt at a constant pressure. And also by definition, you know this quantity d bar q by dt at a constant pressure is Cp. So now equation 3, equation 4 becomes, that means we are using our concept of concept we have used in equation 3. That means this quantity du by dt at a constant volume we have written as Cv. That means using equation 3, that means this quantity, in 4 we get this quantity is Cp, this is Cv. So Cp equals Cv plus du by dV at a constant temperature. This is du by dV at a constant temperature plus P into this dV by dt at a constant pressure. And again, you can now change this Cp and Cv to this side. So Cp minus Cv you are getting as dV by dt at a constant pressure here into P plus du by dV at a constant temperature. And for 1 mole of a gas, for 1 mole of a gas, you can write as PV equal to RT. For 1 mole of a gas, generally you can write as PV is equal to RT, and the general equation is PV is equal to nRT. And taking differentials, we get it as you are taking n as 1. P dV plus V dP equals R dt. Then, if you differentiate this expression with respect to T at a constant pressure, what you get? This P is constant, so P into, you have to differentiate this V with respect to T. That so it becomes dV by dt at a constant pressure. So P into dV by dt at a constant pressure plus here dP. P is constant, so dP is 0. So there is no this term. R into, you are differentiating this with respect to temperature. So this is clearly 1 dt. Then P into dV by dt at a constant pressure you can write as R. That means this term is R. And now you are left with this term, du by dV at constant temperature. There, we will use this concept. Since in isothermal process, the internal energy remains constant, we can write as du by dV at a constant temperature equal to 0. That we have, that means U is a function of temperature alone that we have mentioned. So at a constant temperature, there is no variation for U. So du equals 0. Therefore, du by dV at a constant temperature is equal to 0. Therefore, you are getting the expression as Cp minus Cv equal to R. And this is equation generally known to you, and it is known as your Mayer's relation. The volume expansivity beta, this is also already defined. That means change in volume per unit degree rise of temperature at a constant pressure. This is the equation. That means change in volume dV per unit volume 1 by V here per unit degree rise of temperature you are writing as dt at a constant pressure. Therefore, you can write V beta as dV by dt at a constant pressure. And by definition, we have d bar q by dt at a constant pressure is Cp. So you can write as Cp equal to Cv plus, this equation is here, du by dV at a constant temperature plus P. So this quantity, dV by dt at constant pressure, that means this thing, dV by dt at constant pressure. These are here. So you are writing it as this quantity as V beta. So already also you can write as Cp is equal to Cv plus du by dV at constant temperature plus P into V beta. And on multiplication, you can write it as, that means you are expanding this Cv plus du by dV at constant temperature into V beta plus PV beta. Therefore, this thing, that means du by dV at constant temperature, you can write as Cp minus Cv. Cp is here, Cp minus Cv. Again, this to this side minus PV beta divided by V beta. Or you are dividing with V beta, this becomes du by dV at constant temperature is Cp minus Cv by V beta minus P. So, by applying your first law, you can have an equation like this. And you can derive your Mayer's relation. And that's all in this lecture.